All right, welcome back, everybody. It gives me great pleasure to introduce to you all the great and powerful Andy Eva-Dale, who will be taking us on a deep dive into the UK Power Networks website, multi-award-winning UK Power Networks website. So everyone, please be upstanding with a huge round of applause for Andy.
Hi, everybody. I am neither powerful or great. I just want to let you know that before we start. So I'm going to kick off things today with a quote, and it's my favorite quote in tech. It's actually not a tech quote, but it's from Eric Shintaki. He is a general and the 34th Chief of Staff in the US Army, and it is, if you don't like change, you're going to like irrelevancy even less. And that's a good place for us to start with where UK Power Networks were before we started this project. Now, don't worry if you haven't heard of UK Power Networks. Neither have I before I started working with them. UK Power Networks, or UKPN, and I might use the two phrases interchangeably, are a district network operator that run the energy network for the south, the east of England, and London. They cover 30,000 square kilometers and roughly 8 million customers. So our story begins in February 2022. This was the year we were all coming out of COVID. The whole world was waking up after COVID. It is also the year that Russia invaded the Ukraine, and a relatively small, unknown company released the first public version of ChatGPT. Anyone guess who that was? It was also the year that Storm Eunice ravaged Europe. In the UK, we had record-breaking winds of 122 miles an hour. And don't worry, guys, for anyone on the continent, I've got your back. That's 196 kilometers an hour for you guys. Hope that helps clarify things. And it was the most powerful storm we'd seen in the UK since the Great Storm of 1987. Now, these high winds caused trees to fall down and power lines to fall down, and it was the most damage of any storm in 30 years. 720,000 customers in the UK Power Networks region were left without power, and some of those customers are vulnerable customers that need power to run vital life support equipment, so it's super important that we restored power as quickly as possible. Now, the website itself is a key channel for reporting power cuts. It also looks after something called PSR, which stands for the Priority Service Register. And this is where these vulnerable people can reach out for help if they need it in an emergency. As well as customers, the site also provides key information for media, TV, radio outlets, and MPs and government. So the storm itself lasted for 1 week, and it took a week for them to restore power. And in the period between Friday, the 18th of February, and Sunday the 20th, the website had 3.2 million unique visitors, and the existing system was unable to cope. So, in tech, we all love an acronym, right? And I've invented an acronym here, and if any of you use this, I'd like you to use the Harvard Business School of referencing and use my name underneath it. But UK Power Networks found themselves in the SHIT. Their existing system was unable to S, scale, and it couldn't H, handle major events, which resulted in a week-long I, incident, because of the volume of T. Anyone? Traffic. Thank you. We didn't rehearse that. The existing system started to creak around 2,000 concurrent users. That's 2,000 users on the site at exactly the same time. And it ended up in the UK Power Networks switching to something called the DR site, the disaster recovery site. Now, this site here has really slimmed down functionality, none of the support needed for vulnerable customers. You're unable to report a power cut, but it could handle high volumes of traffic. The internal UK Power Networks team quickly rebranded the DR site to the high capacity site. And guess what it was built in? Well done. I thought there might be more people hazard a guess at that. We are at an Umbraco conference. It's not only major events like Storm Eunice that meant we had to go to the DR site, the high capacity site. Also, if there were major network failures, we had to switch over to it, or nation-level threats. Now, I mentioned the war in Ukraine, and UK Power Networks are a DNO. So they were target for nation-level threat actors trying to cause disruption in the UK. And as a result, we'd find ourselves under extreme load and malicious attacks and ended up on DR. Now, it's disclaimer time. We didn't build the existing solution that struggled to cope with this. We took over support of it the year before, and it was built in Sitecore. Boo. Don't worry, I'm not going to spend ages on this, but the Sitecore solution was riddled with issues. I'm going to run through the top-level stack. I know this isn't a Sitecore conference, so please bear with me, and I'll be as quick as possible. But the infrastructure was all IaaS and on-prem. It cost an absolute fortune. It cost over £100,000 a month to look after the infrastructure alone to host Sitecore, not all the APIs or anything like that. Mad, right? Think we could do £100,000, do more things than run a Sitecore site. That's for more fun things than run a Sitecore site, that's for sure. Change management was really manual. Rollback was really complicated. The ingestion layer itself had to consume power cut data from downstream systems. It could only handle 8,000 messages per hour, but Storm Eunice, we saw like 20,000 messages. So we weren't able to cope with the volume of data coming in downstream. So it wasn't just Sitecore that was breaking, it was also the ingestion system for trying to process all this power cut data. And power cut data has to be processed in order. For example, reported a power cut, engineers en route, engineer on site, issue resolved. If you process those messages the wrong way around, you will affect the validity of the data, which is obviously going to be a massive problem for the end user. In addition, all of this data was written to an old clunky SQL server that was also cost a fortune, and it was using like really inefficient store procedures. So these are some of the things we had to solve. Next up the stack was the API itself that served up the power cut data and a bunch of monolithic services in the background that were providing data and querying SQL. Now, these monolithic services were unable to scale, and the main one is the power cut service. That's the one we're talking about here. This is the one that we really cared about, because it's the one that's providing the power cut data to the end user. This monolithic service itself didn't just handle power cut requests, it also handled PSR requests, reporter power cut, form submissions, a whole bunch of stuff. Also, the service itself, when we received post requests to it, had a fire and forget methodology. So if there's an issue with a downstream system, we just fire and forget. But like that data could be lost, and there were cases where we had issues with downstream systems, and important messages like PSR requests for vulnerable customers were lost. Lastly, the API itself could handle around 3,000 requests a minute. Then we started to run into SNAP port exhaustion, which I'm sure some of you experienced before. And that means that you run out of SNAP ports for the back end and the whole thing falls over. So some problems there as well. Lastly, Sitecore itself, as I said before, it could handle around 2,000 concurrent users. The business required 20,000 concurrent people. That's 20,000 users on the site doing the same action at the same millisecond. So there's a big, vast difference between what we had and where we ended up. In addition, Sitecore itself cost £106,000 a year, and it also had a dam in it. It was $30,000 a year. So it was like lots and lots and lots and lots of cash, like huge volumes of cash there throwing at this, and it didn't work. And to add insult to injury, the editors were completely afraid of making content changes. They didn't know how it worked. They wouldn't want to make changes without us being on hand to support them through it. And they were just frightened of it. They didn't know how to make changes in Sitecore. So to summarize, we had Sitecore. It's complicated, expensive, not fit for purpose. We had a bunch of on-premise and IaaS infrastructure that couldn't scale. Our ingestion pipeline for power cuts had to be handled sequentially and was unable to handle the volume we saw in major events. The front end couldn't handle the amount of traffic we saw. And form submissions would be lost if we had downstream issues. We needed a strategy, and this one is from Sun Tzu. It's strategy without tactics is the slowest route to victory. Tactics without strategy is the noise before defeat. Enter Mac. Here's our strategy. Now, this isn't Return of the Mac. This isn't Apple Mac. This isn't mac and cheese. This stands, I wish it was mac and cheese. I wish my talk was on mac and cheese. Sorry. This stands for microservices, API first, cloud native, and headless. And its architectural principles around composing decoupled systems. Now, we're going to run through each of these guiding principles in turn and start talking about some architectural patterns. And a bit of a disclaimer time again, there's going to be a lot of boxes and arrows. I'm going to check in to make sure you're okay, but you might be fatigued by the amount of boxes and arrows you're about to see. Starting off then, Mac microservices. So we had our power cut data downstream. It was being ingested by a single ingestion service that was writing to SQL using some really clunky store procedures. Then there was a monolithic service for power cut data that was also handling PSR requests, forms requests, report power cuts, yada, 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 yada. And that was being exposed via an API. Now, first things first, we took the monolithic service and we decoupled it into individual services via domain. So now they could scale individually and we could scale them up with business needs, and it wasn't all tied to the power cut service. So we could scale up form submissions separately, et cetera, et cetera. Next, we took SQL. And we swapped it out for Elasticsearch. Now, Elasticsearch does a few things. I guess, first of all, it's incredibly fast reads, but slightly expensive to write to. So the write times are slower, but that wasn't a massive concern for us, but reads were super quick, and that was really important because we wanted to get the power cut data to our own clients. Then we took the ingestion services, and a few things we did here, but the first thing we did is using the power of Docker and Kubernetes. I'm going to talk about Kubernetes later on in the talk. We created multiple instances of the power cut service that were handling power cuts based on their ID. We had 130 instances of the power cut service, all running in parallel, meaning we could process huge volumes of data. Rather than having one single instance that was churning through them in order, we split that up using containers and Kubernetes, which we'll talk about a bit later on. Now, next, I want to talk about a quote from Martin Fowler. He's a bit of a hero of mine, but if there isn't a queue, it's probably a bug. And I think that's a fantastic way to think about enterprise architecture. Now, about 10 years ago, I was an Umbraco developer. I wasn't a very good Umbraco developer, I'm not going to lie to you, but I was all right. I was all right. And then I got this book. It's the Patterns of Enterprise Architecture, or Application Architecture by Martin Fowler. And this was a game changer for me. This is when I started thinking about decoupled systems, design patterns, enterprise architecture, and this book literally did change my career. Now, I want to give it away today as well, so whoever comes and asks me the best question afterwards, this is yours. If anyone asks me a question afterwards, it's yours. So we're going to go through a couple of common enterprise architectures now. The first one is ETL pipelines. So this is how we handle power cuts. And ETL pipeline stands for extract, transform, and load. And this is a really good way of handling event-managed systems or decoupled systems. So we take the power cut data in still. We have our single subscriber to put to it. It's coming in through, this was coming through service bus, so a queue. So we're subscribing to this queue. We would then publish that item onto our own queue, again, service bus, and then subtract that using our transform pattern, where we'd add some of our own business logic to the data coming from the back end. So at this point, we take the power cut data and we'd enrich it. And you've also got the pub sub pattern here, which is a classic pattern for using queues and doing like event-driven architecture. And lastly, we had our load. So this is where we're loading into SQL, into Elasticsearch using our containerized Docker system. We have our 130 different containers running. So this the ETL pipeline is something, an architectural pattern that we use lots at Tangent. Every time we're consuming data and we want to create enterprise systems, we start with this pattern. And it's an absolute lifesaver, being able to process in order, create resiliency, and be able to handle large volumes of data like in a sensible manner. The next one is the eventual consistency pattern. Now, I talked about the issue of us firing and forgetting data. So this is where we had our API requests come in and we're posting a request. It could be a PSR service request. It could be a report of power cut. At this point, again, we use the pub sub pattern. We pop all of our requests onto a queue, and then we have a service that we'll call our own downstream service. Now, if that receives a 200, everything's absolutely fine. But the minute there's an issue with a downstream service, the items pop back onto the queue, and we will try and process it a number of times. That's a threshold you set in Azure for Service Bus. And at the point you reach that threshold, say for example that downstream system's down for a while, you put it onto something called a dead letter queue. And this means then you don't lose the data, so haven't got that fire and forget strategy. You're not going to lose somebody's like PSR request that's sitting at home in the dark, like really needing help. You're still going to have that data. And engineers can then go into the dead letter queue, figure out what's going on. We can then find different ways of extracting that manually and sending it to downstream services if we need to, or people that need to support. But it's like a much more resilient way of handling data rather than firing and forgetting. That's the eventual consistency pattern. Right, on to API first. So we had our downstream power cut service, we had our ETL pipeline, we want to know what that means now, and we had Elasticsearch. We then have our two separate services. We have our address service and power cut service, and these were designed to scale. So they had like 4 instances running at minimum, and they could scale up to 10 under load. Now, these were exposed using Azure API Gateway, and then in front of that, we used a CDN. We used Edge.io CDN. And the advantage of this is we could cache responses on the edge, meaning they could return them really, really quickly. And we set a cache time on the edge in the CDN of the API responses for 1 second. That means we have a 1 second lag for any data we're showing the client, but also means we're only making 1 request every second to our downstream services. So suddenly, if you've got 20,000 concurrent users going through at a single point, still only making a single request a second. And we cached all of the power cut data for the whole of UKPN on the edge, meaning the clients could then consume straight from the edge rather than having to call downstream systems and having to scale and scream and suffer during high amounts of load. Moving on to cloud native now. I don't think you can talk about cloud native without talking about the CNCF, the Cloud Native Compute Foundation. This is an independent organization that has tons and tons of different projects donated by the likes of Google, Red Hat, etc., etc. And the most famous project is Kubernetes. Now, some of you might have seen my talk 3 years ago, and I told this factoid then, but I'm going to say it again now because I think it's quite interesting. It's really geeky, so be warned. Google originally created like one of the first container orchestration platforms. It was called Borg. And Borg was after Star Trek, the baddies that were like robots and they fly around a big cube, which is probably something to do with it. When they created Kubernetes, they wanted to call it 7 of 9. There was a female Borg officer that worked for the Federation, and they were like, yeah, let's call Kubernetes 7 of 9. But they weren't allowed to for legal reasons. But if you look at the Kubernetes logo, it's a ship's wheel, and it's got 7 spokes on it. And that's the reason there's 7 spokes. If you don't remember anything else I've told you today, remember that because it's really cool, right? Anyway, so we had a ton of infrastructure to get rid of. We had a bunch of old VMs, some app services and functions that were running the existing APIs, a bunch of like persistence, SQL, NoSQL, some indexes. I won't read through the lot of it because it'd be soul destroying. But we're going to go through now the process we took to migrate all of this over. So first of all, we take something like a service, like a compute service, and we're going to go through the power cut service again. This was at the time running in .NET Framework 4.7. We would then, as I said earlier on, abstract that out into separate services via domain. Step 2, we would upgrade it, and at the time we upgraded to .NET 6, and it's now running on .NET 8. And then we would Dockerize those individual applications, and each Docker application would create a container image. These container images would then be stored in Azure Container Registry, which sets us up nicely now for running Kubernetes and creating a container orchestrated application. So our Kubernetes cluster, and this is really top-level sort of view of what a Kubernetes cluster looks like, and we're going to quickly run through it now. Starting off with the cluster itself, we used AKS, Azure Kubernetes Service. It was hosted in UK South at the time. All of the infrastructure was provisioned using Terraform and infrastructure as code with 4 environments, test stage, prod, pre-prod. And deployments across the environments were run using Azure DevOps and CI/CD pipelines. Ingress and egress. Ingress is all traffic into the cluster, and egress is all traffic out. That's like a good term to know, but all of that was handled using Application Gateway. So all traffic into the cluster was routed through Application Gateway and via a WAF. So security was super important. Remember, we talked about those pesky nation-level threat actors that we probably can't name, but the starts with R. And all traffic came through Application Gateway. And this was also responsible for load balancing between our nodes and our pods, which is the next point I'm going to get onto now. So pods and nodes. Pods are where individual applications run, containerized applications, and they run inside nodes. We had 38 different pods running the domain applications plus 130 things processing the power cut stuff. All of the container images themselves, so this was our Dockerized images, we went through the process before. They were stored in Azure Container Registry, and then they were split across some nodes. So this is where all of the pods are replicated into separate buckets or nodes. We had 2 running our Linux applications, and 1 running a couple of Windows ones that are a bit legacy, but something we were trying to migrate at the time. So this node structure helped us minimize the impact of upgrades and also meant we could scale out. They can horizontally scale. So if we need to scale them to handle lots of traffic, we can scale them out and out and out and out. Next is the control plane itself. The control plane is like part of Kubernetes' internal cluster. It's where all traffic's routed through to the pods and the nodes. And Kubernetes understands the state of these pods and nodes. So it knows how many pods each node should be running and what type they are, and it knows what to expect if it's a healthy system. Now, if one of those pods or nodes becomes unhealthy, it would automatically self-heal. So the control plane will realize that one of the Linux nodes is down, and it will try and bring that up and automatically redirect traffic to the healthy pods or nodes, meaning you have a level of redundancy. And the first type of redundancy we're talking about here is nodal redundancy. We also split our nodes across availability zones. So we had the whole cluster hosted in a region in Azure, which is UK South. Within a region, you have multiple availability zones. These are actually sort of physical data centers that Microsoft own, and we could split traffic across them by setting our individual nodes in different availability zones, meaning we had zonal redundancy. So if there was a major issue of one of Azure's data centers, we don't care. We can split traffic to one of the ones that's working. Well, we do care, but not as much. Next, we started to look at regional resiliency and adding regional resiliency in. At this point, we added a complete replica of the whole cluster in North Europe. So we had 2 clusters running at the same time. We then used Azure Traffic Manager to route traffic between the 2 of them. This offered regional redundancy, and it also offered us green-blue deployments or canary deployments. This means that, say for example, one of the regions was unhealthy, we could automatically route traffic to the healthy one, but also in a deployment, we could deploy to one, test in isolation by routing all traffic to the old version, then switch it over. We have an element of rollback. So if we need to roll back the change, it's really easy. We just point traffic at the old version, and eventually once we're happy, we'll make sure it's all running properly. We can then do this, deploy the code onto the other cluster. Lastly, we had a couple of supporting services for this. We used Application Insights for all of insight into the cluster to make sure we had all of our good information around how they're performing, and et cetera, and we used secret management using Key Vault. H now, headless. Enter Umbraco Heartcore. I bet you were wondering when the Umbraco bit was going to come, but here it is, headless. We're going to start off with another quote. This comes from Abs. He's one of our clients, and we were able to create and update pages quicker and easier, training new colleagues faster using Umbraco's slicker, friendlier interface. Honestly, he wrote that, and he literally knows nothing about CMSs or anything like that, and he was so impressed by how this enabled his team compared to Sitecore. Umbraco is the friendly CMS. That's because of the amazing community, and all of us here today, right? We're all part of the friendly community, but it's also how easy it is to use and intuitive it is to use for users, meaning less training, enabling them to make changes like apps here. So we used Umbraco Heartcore, as I said. We had to consume data from Heartcore, and we used another ETL pipeline, the same pattern we went through before. So we subscribed to Umbraco's webhooks. We can create webhooks in Heartcore for publish events, for unpublished events, and delete events. We then put those webhooks, or the messages from those webhooks, onto a queue, and they were then processed, where we added some business logic in from the UKPN site, and we enriched that with certain data to create inside Elasticsearch, materialized views. Now, materialized views are a complete view in Elasticsearch of a page or a component, and we can version control those. So suddenly in Elasticsearch, we have a complete copy of every single component and page inside Heartcore that's version controlled over time, and we can use that to roll back, chain, and also with the unpublished and delete requests, we only get IDs from Heartcore. We don't get the full message. We will need to invalidate a front end at some point, which I'll talk about in a minute. But we can reference Elasticsearch to find out a deleted page or an unpublished page. So we have our materialized views in Elasticsearch. We then created a search service for site search, and that was exposed via Azure API Gateway. And also, all of those results were cached on the CDN. So we took a big focus on caching on the edge, and this is how we were able to handle large volumes of traffic. We then had Next, which is a modern front-end application framework. It runs in React, it runs in Node, and it's in React, and it's responsible for statically generating pages. Now, this isn't a talk on static site generation. There was one earlier today. But this means that rather than server-side rendering those pages, so every request going to a server, it producing HTML and sending it back across the internet, we statically generate the pages on change inside the CMS. So on a publish, delete, or unpublish, we would then statically create those pages, and they would be cached on the edge, meaning we can handle huge volumes of traffic, and our downstream systems only get the traffic for the initial cache miss before the CDN's hydrated. This is how it looked. We had a brand new stunning design system. We incorporated a storm mode feature to it that we could switch to in the storm events, which had like a dedicated storm center page, providing updates on the whole region about how the storm was going, how many people were without power, how many people were being restored, etc., etc., etc. And there was a much improved IA and CX for PSR users as well, meaning they can access the service that they need to and the information they need to if they're in trouble. We created individual pages themselves for showing the power cut data, which were providing real-time or near real-time. There's a 1-second pause on the CDN. Power cut data on how up-to-date your power cut request is, and this took significant impact off UK power networks call centers. So they have call centers, and it reduced the number of calls coming through. So back to our original issues. We had Sitecore. It was expensive. We had the on-premise infrastructure, et cetera, et cetera. So Sitecore, we replaced it with Umbraco Heartcore, and this solved our problems. And we saw some staggering results in terms of cost, scale, and scalability in terms of the architectural approach we took. Next, our IaaS and on-premise infrastructure and some of our old PaaS stuff. We changed all of that to Kubernetes. We then used ETL pipelines to ingest all of our data in an enterprise-level manner. We used Next and static site generation to handle high volumes of traffic on the edge rather than sending it through to server-side rendered apps and only being able to handle 2,000 concurrent users. And then to solve the problem of sending form data to backend systems and forgetting about it, we used the eventual consistency pattern. So back to our quote. If you don't like change, you're going to like irrelevancy even less. UK power networks didn't have much choice to go on this digital transformation. They were in the SHIT, as I said at the start, but that doesn't mean they weren't brave. This is a vast amount of change for any client to go through, and they were incredibly supportive, and here are some of the results. Firstly, we reduced license costs and hosting costs by 66%. The project itself will pay for itself within 4 years of being in production, which is huge, right? So it's a value add. Next, from a performance perspective, we soak tested the site up to 40,000 concurrent users. That's, put it this way, google.co.uk's search button gets around 30,000. So using the power of Edge and things like Edge.io, we can deliver like incredible volumes of traffic. It gets a bit pointless at some point. You're literally just throwing money at Edge.io testing a CDN, but it's not still fun, but not encouraged. Downstream messages, we had the issue where they wanted to be able to consume 20,000 messages per hour. We can now consume 100,000 messages per hour using our Kubernetes separate app consumers running in parallel. On the awards front, this was 7 awards the other day. 2 weeks ago, we were in London for the National Tech Awards. We picked up another 2 for Best Enterprise Solution and Best Utility. But the pride there is obviously the Umbraco's Jury's Choice one, which every time I think about that brings a little tear to my eye. I'm excited about seeing who gets tonight's Jury's Choice one as well. And then lastly, a subject that's very close to my home is carbon. This is a stat that some people will have heard before. But the old home page used to produce 1.44 grams of carbon. With the new architecture, the exact same DOM elements, so this is like the same design, everything before we moved to the new design, produced 0.2. This is a fair comparison. If you looked at Storm Eunice and you took that 3.2 million users, just homepage traffic alone in that one weekend would have been the equivalent of 9 flights from London to Copenhagen. So there's a way of like comparing what that would actually mean in reality. 3 key takeaways. First one, Umbraco Heartcore can be used as an enterprise CMS, and it's about how you implement the solution. And I would actually say that it's the most easy and friendly CMS to use. So like there's massive benefits over some of the other products in that enterprise space. Next, Mac architecture will deliver results. It will be able to scale your applications, drive down costs, and create more resilient applications that also are carbon friendly. And lastly, start using enterprise design patterns today. It'll be the next step in your system and in your careers. We've got a report here. The slides will be available. If you want to download this, there's some more detail in how we achieved this for marketers, operations, and tech. My name's been Andy Eva-Dale. I'm the CTO at Tangent, but I can't take credit for this. I'd actually like Mike Sinnott to stand up there, who's our head of development and responsible for this. I'd like everyone to give Mike a round of applause rather than me, because he's the one who delivered this.